I'm given as no class that day. Is there anything that you want me to do about that extra session? I'm usually running with one session buffer because I might get sick. Was never sick actually, since at UCR I never got sick last time, but it could always happen. Or there might be a question coming in class and I need a lot of time to respond to that. And then so, then I would always want to have one session buffer. But now it appears that we are doing really good in time. So what should we do with next Wednesday? Yeah? I could make a review. I did that many times, going through everything. I don't know how helpful it is for you, but if you like it, I can do that. Okay, you are so much active telling these things. So we're going to have a review next week, Wednesday, unless somebody of you tells me something else. And you can send me an email, you can talk to me tomorrow during office hours, and let me know what you would for us to do on Wednesday. Okay, with that, I'm showing here my homework solution, kind of, for the problem. And I'm sure you have very similar looking ones. Or maybe not, maybe I made a mistake somewhere and yours actually look good like that does. But that is what I had over here for my homework. So if I had this A and C in the beginning, they are over here both together. So you only see C because the line for A is right underneath here. And then we also put some E in the beginning, and the E in the beginning then only has the last of the reactions to perform, and so that was decomposing relatively quickly to become our final product F over here. But the amount of G is taking a very long time until we have something over here. And you would need to go to a much longer time step in order to see then that appreciable amount of G is formed, so that you get some of the reaction actually proceeding in the beginning and moving forward, and that of the material which in the beginning was A and C, that is becoming F. So F is an almost total conversion of what we put in as E, but then only very slowly through the sequence of reactions you are getting some material. Okay, that will be the case. And I'm sure you analyzed it in a similar way, and then I asked you to do some extra work for putting in, looking at the DA or something like that. But what I want to cover today is a neat feature of Excel in the beginning. And because in most cases, you don't really have perfect rate constant. In most cases, when you work in a lab, you might want to establish what are actually those rate constants. So you might have a faint idea of what they could be, and you might have an idea of what the sequence of reactions might be. But you only have an idea. And so you don't know precisely how big those values for Ka and so on, how big they are. You only have approximately an idea, and that's the idea you write there. But as chemists, what you can then do is experiments and just see what will come out. And now if you as a chemist were to do experiments and say, okay, I know precisely, I measured it, I know I had A, C, and E at 0.3 moles per liter in the beginning, and then I'll measure the concentration of F. And you might measure these points over here. They don't look perfect over there. There will be some error in this measurement. We also realize that these points here, and all the F which is being produced in the beginning, is really being produced just by this last reaction step, that the E is being converted into the F. So the first steps of the reaction aren't really so important. So what are you going to do? How are you going to figure out what is the real rate constant for that, even if you have a complicated system? Now what you're going to do in such cases, I hope, is And if you have the time over here, and you have here these actual values, the ones which you measured, then you can try to look up in this table over here, what do you expected from your original K values in that case. And so let's call it numeric over here. The way you do that is that you use a routine of Excel which is called VLOOKUP. And in VLOOKUP, you are trying to find the value at this time over here, and you are using as the range where you were interested in this range, which has a time on the left column, and put that down here so I can see myself. And then we are interested in the value f, not time. That is the first column, a is the second, third column, fourth column, fifth column, sixth column. So we are interested in the value in the sixth column, and we don't need to have a precise match, but just the first match where they're above. And then Excel will see where is 0.1 in this timetable, where is 0.1 in this table, and it will find you the value which is at 0.1 over here. And then if I just put this down here, I get the values at the other times. So here I will have the values now for the F's which I saw predicted. So, and I can then see what is my difference between them. I can say, okay, what's the difference between the actual measurement and the predicted value? And that might be something like the absolute value of this minus that. And I put in the absolute so that it all becomes positive numbers. And then I can say, okay, how much is my total error? And that is, of course, the sum of these ones. You just say, yes, the sum of those. Okay. What equals sum of okay, so that is the error I'm making. And of course I want that error is the smallest possible. I want to have my K values being really nice. And in order to do that, I can now tell Excel, do the work for me. I can now say, go to the data column and then use the solver. The solver is like analysis tools, where you had the histogram earlier. By default, the solver is not installed in Excel. So if you want to use the solver, you need to install the solver just the same way as you install the histogram by going in Excel here to File and then down Options and so on. But if you have the solver installed, then I can mark the cell over here, and then I go to the solver, and I say the objective, and the objective it already puts to U12 over here where I have my cell, otherwise I would choose that. And I want to have this objective being minimum, I want to have minimum error for that. And I tell Excel that the values it can change are my rate constants, which I have over here. And then I tell it to solve things. And you see Excel, even on a nice computer, it takes a little while fidgeting with the numbers on that. But after a while, it is done, and it makes my error much smaller than it used to. So it's not perfect in that regard, but it certainly adjusted now the rate constants K, that I have a really nice fit over here for F in the values. So if ever you want to have something complex fitted, if ever you want to have something fitted in Excel which is not part of the fig functions which for the trend line which Excel allows you to choose, then the solver is the way to go. With the solver you can have whatever kind of problem in Excel, you can have whatever kind of setup for complicated rates, and then you can ask solver how good, what is the best values. It is good for solver to be already close to the right solution. Solver is trying to start out from the solutions you bring and then modifies them a little bit and sees in which direction is it getting better if it modifies. So if you have completely random values there for K, it may not find any reasonable solution. You need to have already somewhat reasonable values for that. How would you do it? But array the problem in pieces. So for instance, in this kind of case, I could first just say I only want to change the KC and the minus C, which is really the only thing to change in this case. Because the first ones don't really have an impact in the beginning of the reaction, because right now the production of F is really only out of the E which we put in here, so it only changed those. But break it into pieces, see that for smaller reaction steps you have information, get approximate values for the case that way, and then you can solve the more complex system of reactions in Excel. So Excel can allow you to, in that way, validate any kind of system you have. So if you don't know what the real sequence of reaction were, but you measured the concentrations of a couple of those reactants and products, then you can test out many reasonable ways how the reaction might proceed and see for which setup you can get Ks which match your reactions. And then whether you can get a good match of the evolution of the concentration of all reactants. And if you can, then maybe you figured out the right elementary reaction steps. And if you can't, then it might be an indication that you should try a different sequence of reaction steps to be what is underlying the overall reaction. So by this numerical analysis, this kind of fitting, the kind of seeing, can I solve the concentration as a function of time under the assumption that I have this or that setup of elementary reaction steps, you can actually figure out what are the elementary reaction steps, what's a reasonable succession of them. You can only do so much that way. You need to have some chemical knowledge about what they are, but if you have some chemical knowledge and it's just between two different pathways or so, then often you are able to use the solver to figure out what pathway was. You can also use the solver for much easier questions if you just want to say, is it a first order or is it a second order reaction? And then you can also see in which one do you have the better fit for K. You can also do that with trend lines very quickly. But that is how you can use kinetics in order to gain knowledge about the system. Okay. At this point, I think I'm done with what I wanted to say about kinetics. Kinetics has many important roles in chemistry. One of them is figuring out how fast to make your product. Then it has to do with controlling that you get the right product and not byproducts or anything else. And then, as we see it over here, kinetics also allows us to learn something about elementary reaction steps. If we know how fast reactions proceed and how they respond in their rate to whichever concentration of reactants, then we can learn from the kinetics of a system. What are the elementary reaction steps? How will the reaction proceed? How can we manipulate those reactions in a chemically meaningful way? Okay. Are there any questions at this point about kinetics? Okay, that seems not to be the case. Then let us go into the next chapter, which is about something related, but only related and not the same. And that is, we need to talk a little bit about transport at this point. We need to have a better understanding of what is underlying how things move in chemistry. See, if you work in a solution phase chemistry, you probably put a stir bar in. And there's a reason why you need that stir bar. And what would happen without the stir bar? There's even a reason for how fast that stir bar should be stirring. And there are many other places in chemistry where transport of things is crucially important. And so we need to have a good understanding of what governs transport of molecules. Not just, oh yeah, they're kind of moved around, and we already know molecules are really fast in the gas phase. They move with the speed of fighter jets. So they move like 600 miles per hour. Molecules would get a speeding ticket on the freeway for sure. But if they are so fast, why do we need a stir bar? Because aren't they moving through that beaker, zipping through that anyway so fast? Or put it in a different way, why do we need to breathe? If the molecules in the gas phase here in this room are moving with the speed of fighter jets, why don't they get into and out of my lungs really, really, really quickly, so that I don't need to inhale and exhale, and so on and so forth, in order to change the air in my mouth. Why don't they just do that by themselves? So when you need to kind of move things but by yourself rather than by themselves, when you need to breathe, inhale and exhale, and when don't you need to breathe, when is it taken care of by the motion of the molecules? When you need to stir and when you don't, you need to stir. When you need to pump something and when you don't need to pump something. And can I practically pump something at a certain speed, or is there no way that I can pump something so fast? All those kinds of questions are really relevant in designing reactors, designing reactions, being successful as a chemist. And so we need to talk about it. People thought about that for a long time. This is a quote from more than 2,000 years ago, where people thought about what are the smallest particles, and are they stationary, are they moving? And Mr. Lucretius observed dust motes in the air on the day when the wind was still. And he observed that in the sunlight, those dust motes were reflecting the light, were sparkling a little bit. And even though there was no wind at that time, they still moved. And he was quite astonished by it. What makes them move? What do they? How big are really the particles that are moving? Do those moving dust motes tell us that even when the wind is still, when the air is still, when there is no wind, that there is motion in the air? And nowadays we can ask ourselves, yeah, what does it really tell us about the molecules or the small aerosols, as we would call those dust motes now, he was observing. So what can we find out about this? And so let's talk about the fusion first. So the fusion is a process which we described as our gas particles earlier. If the gas particle is moving around, it is moving at high speed, but it's not going for an appreciable distance in a long straight line, because we realize that like every 100 or every 1,000 times it goes across the box of volume belonging to its neighbor, and will actually hit its neighbor and be repelled and reflected back, and so it will go forwards and backwards and forward and backwards, bouncing forward and backward and bouncing forward and backward. and never potentially getting really very far. Obviously, not every gas particles is moving with the same speed. Some of them happen to hit the nearest neighbor, and then the nearest neighbor as well, and so they essentially stay stationary, just bouncing forward and backwards. Others are more lucky and just whizzing by the nearest neighbors for a couple of distances before they have a glancing hit and then almost move on further in a straight line. So the answer to the question which we are asking over here, how far do molecules get by diffusion, is not one of the style, every molecule is going the same speed or every molecule is going the same distance in the time, but rather one of statistics, one of averages. So the average diffusion distance, the average distance a molecule gets is of course zero, because there are just as many molecules who get some distance in that way as in that way, and so it averages itself out. There is no preferred direction in nature. In every one direction, the molecules will get the same distance if they diffuse in air, if they diffuse in water. So the average of that will be zero. But we realized already earlier that the RMS average, or at least the average of the squares, is different. Because if I first square the displacement the molecules were doing, then all numbers are positive, and so they won't average out anymore to zero. And so it's a reasonable question to ask, what is here the average of the square of the displacement of a molecule as a function of time? How far will they get on average? And that square, this value over here, if you think about the Gaussian distribution of how far they get, where the distance is on the x-axis, and the probability that they got so far on the y-axis, then that x squared is closely related to the full width of the function at half of its maximum. So we can try to figure out how far they go. And believe it or not, when Einstein started out, his PhD thesis was on the structure of the sugar molecule, so he was really a chemist starting out. Then he worked a lot on statistical mechanics problems and thermodynamics problems, like this one of them. So what I'm presenting over here is the Einstein-Smoluchowski equation. In English, you might pronounce it Smoluchowski, but Smoluchowski is what he would call his name. And it's shown over here. So the average of the square of this, the mean of the square of displacement of molecules, which just move around by diffusion, by their thermal motion, bouncing against the nearest neighbors, is given as 2 times the material constant, which is called the diffusion constant, times the time. So this is not your normal kind of dependence of the velocity on time. So if you have a constant velocity, then you would say, okay, if I wait twice as much time, I'll have twice as much distance. This is not what is going on here. If you wait twice as much time, you only have a little bit more distance that the molecules move. Because the linear relationship is between the square of the displacement and the time. So the actual displacement, not the square of the displacement, the RMS displacement, if you want, the root of the mean of the square of that, that is the root on this side then, and the root on this one here. So the displacement goes to the root of the time. Big changes for small times, small changes for large times. And that tells us something. That tells us something that somehow there must be a sweet spot in between where they are similar. In the beginning, the root is really steep, and then later the linear relationship is really steep, and then somewhere in between they are the same. And it turns out that biology is just looking up on Earth, is that average? Where are they about comparable? At which size? And that is where life is. So if you look at microscopic life doesn't need to breathe, doesn't need to inhale and exhale. Bacteria don't inhale and exhale. Even insects don't, some of them at least, don't really do that. Because they are so small that they don't need it. Because they are where this root over here is a steep function, where you have lots of motion by diffusion. And then there are bigger animals like us, where we already are on a size scale where our lung is sufficiently far away from our nose that we need to move some air. And so we adjust at that place where the root gets here not so comfortable anymore. And then so we need to develop the art of breathing because we need to transport things. But the point is, the diffusion constant, which Einstein and Smolowski described over here, this diffusive motion, determines a lot about how everything is anything in life and in chemistry. This has to be sized. So it's really important. So if I were to talk about diffusion in liquids, then the diffusion is way, 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 way slower. Liquids are still fluids, just like gases, so it's not fundamentally different, at least to some degree. But it is certainly much different. If you have a liquid like this one over here, then you'll see that the bouncing around there, always in contact to the nearest neighbors. They always feel the nearest neighbors. Liquid is a condensed phase. In a condensed phase, it means the molecules feel in every direction that there is a nearest neighbor by them. And so the motion is never this ballistic straightforward until they hit. They are always guided in every single portion of their motion by their nearest neighbors in their surrounding. And so you'll find an even much, much slower kind of motion. To illustrate that, those are diffusion constants G for a substance as liquid and for a substance as gas have been mapped. And what I'm showing over here is actually sugar and water. That's the sugar in your coffee, yes. So if you put your sugar in your coffee and you just put it inside there, the bottom of your coffee cup, and you wait 3 hours, it has traveled about a centimeter, less than half an inch. So if you want to get your sugar in your coffee tasted, you really need to stir it. Or you wait on the order of 48 hours for it to travel about an inch in each direction. So that diffusion in the liquid phase is really, really slow. Those are room temperature diffusion constants. When coffee was cold in the beginning here. And they naturally will get up if the temperature is going up, because then the molecules move faster, and so they cover more distance, and then they also have more momentum, and so they're not so much affected by the neighboring particles. They can kind of push through that, and so you will get more diffusion in that way. So diffusion constants are tabulated, and here are tables for diffusion constants. Know that the diffusion constants for the gases over here are in these values, and then it's 10 to the 5 times, so 100,000 times. So in liquid, you need to multiply, is about 100,000 times slower, the diffusion, than in the gas phase. If you have this 100,000 factor or so, then those values are of similar order of magnitude. So the square of the displacement is 100,000 times slower in a liquid than it is in a gas. Does it make sense? Okay. Like that. If we talk about the fusion, we need to have specific words for that. Because the fusion has a lot to do with what is the fusing there. And so we have to look at auto or self-diffusion, which is like water in water diffusion. Or we can say, talk about tracer diffusion, where we have one sugar molecule which is diffusing in a whole lot of water molecules in your coffee cup. And then we can ask ourselves, how fast is that sugar molecule with all those water molecules surrounding them? And then anything in between, any different concentrations. And you'll find that if you look at the dependence of the diffusion constants on the concentration, there's a lot of variation. Let's take very similar molecules. Octane, the main component, if you wish, of gasoline, or the average component of gasoline, and dodecane for carbon atoms more in the chain. And you'll find that the slowest diffusion you'll have for dodecane and dodecanes. Big molecule in big molecules will move slower. It's always kind of hanging up somewhere with this long carbon chain and not getting by, and then so it has a hard time diffusing. It's not getting very far. And then you can say, oh, I vary my composition from pure dodecane to pure octane, but I'm looking at the tracer diffusion of dodecane in that. And that would, of course, be relatively slow up to the value you find over there, which is for dodecane, single dodecane molecule, otherwise a pure octane. And you see it gets like a factor of 2 or so faster over there. If the big molecule only needs to squeeze by smaller molecules, it has an easier job doing it, and it's getting faster. And the fastest diffusion is, of course, if you have octane and octane. The small molecules, and that is going down as the octane is more and more in dodecane. And then you can also look at an average diffusion constant, taking into account what probability you have to the molecules dodecane or octane given by the x-axis, and the correspondingly weighted average between the two. And you will find that curve over there. So diffusion constants are rarely only one number, because you can see they are varying here quite a bit depending on composition, and then they are also varying quite a bit depending on temperature, and then they are also varying quite a bit depending on temperature, pressure. So there are lots of variations, and then it is hard to say, oh, I know that one number. You need really extended and complicated tables, and those tables exist for many substances because, from a technological perspective, diffusion constants are really important. You can also say things can happen. Here you have ethanol in water, and at a certain concentration over here, the diffusion becomes the slowest, because there you have the strongest interaction between the water molecules and the ethanol molecules. And then at different concentrations, you have less interaction between them on average, and you will get faster diffusion. So just measuring diffusion constants, you can actually learn about how many water molecules interact on average with ethanol molecules. Where do we have this optimal size? Where do we have those optimal pairs formed? And we've learned something about the interaction, the hydrogen bonding between those two species. Now, typically, the diffusion constant is proportional to the temperature in Kelvin. Twice the temperature in Kelvin, twice the diffusion constant. Give or take. You probably also remember diffusion from the concept of Chem 1. One of your first chemistry lectures here at UCR was all about diffusion, I believe. It was a Millikan experiment which told people how big is an electron charge. And it was all about the diffusion speed of particles and how their diffusion, the oil drops, the oil mist with the charged particles in the gas phase, how they moved about. So it was really, really important. In fact, it was one of those experiments which allowed people to figure out what Avogadro constant is. It allowed people to see what is something which has to do with R and what is something which has to do with N, and relate them to each other. So the Brownian motion, or the motion of particles in diffusion, had a tremendous impact because it told people how big are atoms. That's really important information. Is it 10 to the 23 particles in a mole, or is it 10 to the 20 particles? People didn't know. And this way, they found that. Okay. Then the fusion can have an effect. If I have one phase and another phase and a barrier between those two phases, and I remove that barrier, then those two phases will probably mix. Say I have an ethanol water mixture on one side, I have pure water on the other side, I remove the barrier, I will get some of the alcohol maybe over here in the green particles move over to the left-hand side, equilibrate the concentration, maximize the entropy in that system. So the fusion has an impact in as much as it equilibrates concentrations. So the particles in the solution move in every which way, of course, down, left, right, and so on and so forth. And if you have many of them, then there are many of them moving on the right-hand side, and few of them are moving on the left-hand side. And if you had a barrier between them, if you had a barrier here between them, then there would be, of course, way more molecules from the right-hand side moving through that barrier than molecules from the left-hand side moving through that barrier. Because there are just more molecules on the right-hand side in the first place. And so there are more which can come from the right-hand side and move across that imagined area A over here, this imagined cross-section. Then there are molecules coming from the left-hand side moving across that because it's just one molecule in the first place. There can't be so many. So if we are interested in the change of the concentration, the flux of concentration, then it is good to think about those imagined cross-sections. So this is now not anymore a real barrier, but just an imagined cross-section. In the beginning, we had very different concentrations. And then over time, at this now only imagined cross-section, some particles from the right move to the left, and other particles from the left move to the right, and we get a concentration which becomes more gradual, and over time it will be even on both sides. So I have a flux of material from the right-hand side in the opposite direction of the slope. The slope is going to the right, the material is moving to the left, correct? So I can start with a differential equation. The differential equation is that the number of particles which move through an imagined area at the position x over here, per unit of time is given by the first derivative, the slope of the concentration over here, with a minus sign in front of it, because the particles move from high concentration to low concentration, not from low to high, times the diffusion constant, and this is the same diffusion constant which we just talked about. That is why in the Einstein-Smoluchowski equation there's a 2, because the diffusion constant was already established for this kind of scenario, and they found they just need to use the established one for equilibration of concentration multiplied by 2, and it would give them the distance times the area of our imagined cross-section. The whole thing here is called Fick's first law. So the flux, the number of particles which go through a cross-section per unit of time driven by a gradient of the concentration is given by a negative sign, the diffusion constant, and the area through which the particles can diffuse. So I have an extensive property of the system, number of particles, and I take a derivative by time of that extensive property, and I relate it to an intensive property of the system, the concentration, of which I take a derivative by the place. Every differential equation where you have the first derivative of an extensive property of the system by time, and you relate it in a linear fashion to the first derivative of an intensive property of the system by the place, is called the diffusion equation. So it's not only the particle diffusion which we have over here, there are a ton of other diffusion equations. Heat transport, charge transport, you know one diffusion equation. Ohm's law for your resistor, it's also a diffusion equation. It also follows the same kind of thing. And we are going to talk on Friday about it. But today, I would like to go a little bit farther so that you can do your homework. And that is, I want to look at viscous flow. That is now also transport, but it's transport not governed by a difference of concentration, but it's transport governed by a difference of pressure. That is wind outside. Wind is difference of pressure, and that makes air flow. That is inhaling and exhaling. There is a difference of pressure inside my lung and in this room, and that makes the air flow viscously up and down my windpipe and into and out of the lung and the room. So if I have such a fluid transport, and for now, let us think about liquids and not gases. Gases are actually really complicated. We are going to talk about them on Friday. But today, let's talk about liquid transport. If I have liquid transport, then that liquid transport goes from a place with higher pressure to a place with lower pressure. And then along that tube, along that pipe, along the connection over there, there is a gradient in pressure. Here you have the high pressure, here you have the low pressure, and the pressure drops along the pipe. I have a gradient of the pressure. Pressure is an intensive property, so I have a gradient of my intensive property, first derivative of my intensive property, and I can directly relate to that to what volume of the fluid, what volume of that liquid is flowing through the imagined cross-section over here. That is my measurement. And I need to put a negative sign here because the flow is in the direction of the lower pressure, from high pressure to low pressure, and not the other way around. It's not flowing in the direction of rising pressure. And so we need the negative sign over here. And then there is a radius here which goes to the fourth power, y, let's wait a moment. And then there is a material constant. First it's a pi, 3.1 and so on, divided by 8, and then also divided by eta, the viscosity. Viscosity like viscous flow. It is the resistance, the friction and material has to flow. Why is it the radius to the fourth power? It's the radius to the fourth power because the radius to the fourth power is, on the one hand side, the radius to the second power. That gives me radius to the second power is proportional to the area. So that gives me the area. And then I still have 2 powers of the radius left. And the 2 powers of the radius left are accounting for this kind of parabola in the pipe. In the middle of the pipe, the molecules which flow in this direction only bounce the neighbors which also flow in that direction. So they are not very much hindered in their flowing in this direction. So they can move fast. But on the side over here, the particles will hit against the tube. And so whenever they hit against the stationary tube, then they are stopped to some degree, and so they flow very slowly. And so you have this quadratic relationship in the middle of your tube, how fast they are flowing, and that gives you 2 orders of R for this dependence, and then you have the cross-sectional area that gives you another 2 orders for a total of 4 orders in R. So this is fluid transport, the amount of volume which flows through an imagined cross-section in a pipe per unit of time is given by the first derivative of the pressure over the distance in that pipe times those factors. And then the viscosity error, there are some representative values for that, which you can look up way more. The whole thing has a name, and it's called Poiseuille's law. And yes, Poiseuille is spelled in this way. You need to memorize how Poiseuille is spelled. There's not a really good reason why it's so complicated, but it's Poiseuille, and he's spelled like that. Okay, with that, I'd like to end, but not before this is a slide of Friday. Not before giving you the homework. And the homework is use Poiseuille's equation. Imagine you have a reactor and you have a boiler. There is some distance between them. There's some pipes in that. At the boiler, there's a heat exchanger, a really thin, long pipe where the water is flowing through. And then there's again a big pipe which brings it back to the boiler. You have a certain amount of pressure. The pressure is used up for pumping the water through the connection pipe and through the heat exchanger inside here, and then again through the connection pipe. How much heat can you transfer that time? And then the homework which I'm going to assign on Friday and Monday, the last homework 16, will be to compare that to heat by thermal transport. But this one here is a homework for Friday. So thanks so much.